All right, let's dive right into this explainer by asking a question that literally every hardware engineer dreads.
Seriously, think about it for a second. What actually happens when a fuse blows inside a completely sealed battery pack? If you have to rip apart a super expensive, tightly sealed electronic device just to replace a tiny, melted piece of wire, well, you've got a massive engineering nightmare in your hands, right? The service costs and the downtime? Yeah, absolutely unacceptable in modern electronics.
To see how we solve this, we're going to take the engineer's journey together today. We'll briefly look at the overcurrent problem, PTC physics, what's inside the fuse, some thermal equations, data sheet decoding, and finally, industry applications.
Starting off with Section 1, the overcurrent problem.
We all know traditional fuses are a one-and-done deal, right? They literally melt themselves to stop the current, leaving a clearly defined open circuit for primary safety. But that means physical replacement. On the flip side, a polymer positive temperature coefficient device, or PPTC, gives us this kind of magical set-and-forget solution. They auto-reset, they can withstand multiple overcurrent events, and they are completely maintenance-free. It's a real game-changer. Moving right into Section 2, PTC physics.
So how do they actually do it? At the very heart of this technology is the Curie point. Now, this is a fundamental concept in material science, where temperature radically alters how easily electricity can flow. When the component hits this specific transition temperature threshold, the resistance doesn't just climb gradually. Oh no, it exhibits this massive, sharp, several order of magnitude spike.
Engineers achieve this sudden resistance spike using two primary platforms. First, we have ceramic PTCs, which rely on incredibly temperature-sensitive materials, like doped barium titanate. And then we have polymer PTCs. These use a highly cost-effective polymer matrix that's absolutely loaded with conductive particles, usually carbon.
Let's picture this at the microscopic level in those polymers. In its normal crystalline state, it acts like a multi-lane highway for electrons. The carbon particles are touching, the paths are wide open, traffic is flowing smoothly. But when excessive current flows and the device heats up to its Curie point, the material physically expands into an amorphous state. Suddenly, it's a massive traffic jam. That volume expansion literally breaks the conductive paths. Then, once the fault is removed, it cools down, shrinks back, and boom, your conductive highway is instantly restored.
All right, Section 3, inside the fuse.
Pulling back the curtain on the actual internal construction, you can see the active ceramic semiconductor body sitting right there in the middle. It's sandwiched between these current-distributing silver electrodes to ensure perfectly even flow. And then the whole assembly is wrapped up in a tough epoxy encapsulation. That protects it from moisture and mechanical stress. It's basically this rugged, highly engineered solid-state sandwich.
Which brings us to Section 4, thermal equations.
Okay, the steady-state behavior of a PTC is governed by this fundamental thermal equilibrium equation right here. Power equals the dissipation constant, that delta symbol, times the difference between the body temperature and the ambient temperature. Now, it's absolutely crucial for your PCB layout rules is that this dissipation constant is heavily influenced by your board. Think about it. If you solder this fuse to thick 2-ounce copper planes, those traces are going to act like giant heat sinks. That actually increases your dissipation constant, meaning the fuse will take longer to trip during a fault. You really have to account for that.
Building on that equilibrium, we use this beast of an equation to calculate the exact time to trip. Essentially, this translates into exactly how long the fuse takes to react to a fault based on your initial power, ambient temperature, and heat capacity. It's a great reminder that this isn't just guesswork, right? This is highly predictable, strictly engineered thermodynamics.
Let's put that math to use in Section 5, data sheet decoding.
Exactly like senior engineers do out in the industry, selecting a resettable fuse is a rigorous, multi-step process. You got to start by defining your nominal supply voltage and anticipating credible fault cases, things like a hard short to ground or maybe a downstream regulator failure. From there, you choose your hold current, compare your ratings, calculate your time to trip, and meticulously verify that operating temperature range.
Now, step 2 is a place where we see a ton of common mistakes. Hold current, or IH, is the maximum current the device will continuously hold at 23 degrees Celsius without tripping. Here's the catch. If you don't pad your hold current with a good 25 to 40% margin above your normal load, well, you're just asking for trouble. Without that margin, and without paying close attention to thermal derating curves, your device is going to suffer from super annoying nuisance trips, simply because the ambient temperature got a little too high on a hot summer day.
And finally, Section 6, industry applications.
So, where do these things actually go? Honestly, these components are everywhere.
We're talking about protecting the complex battery management systems inside EVs, safeguarding field-wired I/O modules on a manufacturing floor, and ensuring life-saving medical devices operate safely and reliably without sudden failures. Sure, traditional fuses might still handle those massive primary high-energy faults, but PPTCs, they provide this quiet, auto-resetting safety net in remote or sealed environments across literally every modern industry.
It's just incredible to realize how much of our modern world absolutely relies on polymers, expanding at a microscopic level. It kind of leaves us with this final thought. If a tiny, super inexpensive component can automatically heal a catastrophic circuit failure without us ever lifting a single finger, what other parts of our everyday technology are secretly fixing themselves right now? Seriously, just how many disaster scenarios are being quietly averted in our pockets every single day?